This is a review of stoichiometry and chemical reactions, along with some information on gases. I've included excerpts of the formula sheet and the different review videos and PowerPoints, just to remind you that there is a lot of really good information that you will have on both sections of the AP exam, multiple choice and free response. So make sure that you remember all these details are there and refer to them when needed. So first of all, as you're going through the PowerPoint, I've really asked you this question, and it's like an animation that reveals the answers one at a time. But stoichiometry is the basis of so many questions on multiple choice and free response that you really need to think about what information is given to me. If I can calculate moles of different, given different information about substances, maybe masses of solids or solution information or something about gases, if you can convert those to moles, then that balanced reaction is going to be the key to convert moles of one substance to moles of something else that is asked about. Limiting reactants are always questions that are asked on any AP exam. Remember, a limiting reactant is the reactant that is used up during the reaction. Whatever beginning amount it had goes to zero. And this is called a completion reaction. So the reaction does end once the limiting reactant is gone. Here's a question just as a practice problem. What is the maximum number of moles of aluminum oxide that can be produced by the reaction of 0.4 moles of aluminum with 0.4 moles of oxygen? I've given this just as kind of a sample multiple choice problem you might see on the AP exam. Notice there's no reaction given, and it's critical that if no reaction is given to you, that you write a reaction. It's telling you the product is aluminum oxide and that aluminum and oxygen gas are the reactants. So when you write this balanced chemical equation, the reactants and products are not 1-to-1 mole ratios, which will help you determine the answer. As you see, I have the balanced reaction as 4 aluminums and 3 moles of oxygen yield 2 moles of aluminum oxide. Again, there's several ways you can work at limiting reactant problems. One easy way that tends to give you many answers that are asked is to convert each reactant to moles of the same product. So in this case, it's an example where by doing that, you actually have the answer you need. So notice the mole ratios are 2 to 4 for the aluminum as the reactant going to the product, and then 2 to 3 for the oxygen gas. So therefore you see that 0.2 moles of aluminum oxide is a smaller amount of product that would form, which would come from the limiting reactant, because once all that aluminum was used, there would be no more left at the end, so we would choose the answer B, 0.2 moles. Other calculations related to moles or determining the formula of an unknown compound. An empirical formula is the simplest whole number ratio, and I'll give you an example of CH2. Those subscripts can't be reduced into any simpler form. And then a molecular formula is some multiple of the empirical formula, and a molecular formula could also be empirical. So many times, like as I've given you with this example of glucose, you notice I would have had to have taken this empirical formula and multiplied times 6 to get the molecular formula. But there are cases where the empirical and molecular formula are one and the same. Here's a handy little rhyme that I got from a friend that would help you remember this. The steps to take: percent to mass, mass to mole, divide by smallest, make it whole. These are steps that would help you remember the math that would be associated with determining the formula of an empirical, the empirical formula of a compound. As you notice, here's another example problem. It gives us a mass of sulfur and a mass of fluorine. Notice the rhyme starts off with percent, but we already have masses, so we can just skip right to that second phrase, mass to mole. So our goal here is, even though we don't have a calculator, the numbers are set up so the math is simpler. We can look up on a periodic table the molar mass of sulfur, which is about 32, 3.21 grams of sulfur divided by 32, and then we'll take 11.4 grams of fluorine. Its molar mass is 19. So the math there is not quite as easy, but if you notice, if I go to the next slide, I've set this up so you can see the work I've done. Notice 3.21 divided by 32 gives me 0.1 moles of sulfur. And then the fluorine's, again, a little bit more cumbersome, but again, you're expected to round. So if I rounded down and rounded 11 grams of fluorine to 10, and then rounded the molar mass up, again, 11.5 or 11.4 over 19 is a little bit more than half. So I know that when I do this math, that the answer that I would get, as you see I didn't give you a specific answer, I just said it's got to be more than 0.5. The next part of the rhyme says divide by smallest. So obviously the sulfur moles are smaller. I would divide that into both of those values. So sulfur in the formula would have to have a subscript of 1. You're going to notice all the answers have that. But then just knowing that the answer would be 0.1 into a number greater than 0.5. Notice there's not even a subscript that is a 5, so our answer would have to be D, because it would be closer to 0.6. Isotopes are a topic you might remember from your first year chemistry class. Atoms of the same element with different numbers of neutrons, so the neutrons are what gives them the different masses in the compound. As you look at this graph, you can see that this element has the highest percent of abundance of an atom with a mass of 24, and then 25 and 26 have similar percentages. The 25 mass is a little bit smaller. The masses on the periodic table are called weighted averages, or the average atomic mass, and these are coming from these percents of abundance. So the element this is, as you can see, it is magnesium if you look on the periodic table. Even though there are isotopes of 25 and 26, we can see that since the 24 mass is so abundant, that the average is weighted towards that. So I've given you the example of how you would calculate that. Again, I had to estimate these percentages, so I said it's about 78%, 10%, and 12%. And so I've changed those to decimals, multiplied times the corresponding mass, and then added all those products together to get about 24.34, which is very similar to the molar mass of magnesium. For gases, expect to use PV equals nRT at least, definitely once in free response. Over the past 4 years, there's been one question every free response where you were expected to use that to solve. So, just watch for a reaction that's, maybe a gas is produced or there are gases in the reactants. Again, obviously you're only going to use PV equals nRT for a gas. I put watch the units because on your formula sheet you are given several values of R. Make sure you use the correct one. There are 2 on the formula sheet, 0.08206, that involves atmospheres as the unit of pressure, and then there's another value, 62.36, that has torr. So either one of those would be a good choice depending on what pressure units were given to use for PV equals nRT. The other value is 8.3145. It does have joules. That would not be a choice you would use here. Collecting a gas over water. Again, I've addressed this at the end of the PowerPoint as well, but the key here is you would be given the water vapor pressure, which you're expected to know that since any gas that's collected over water would also contain some of the water vapor contributing to the pressure, that you are expected to know to take atmospheric pressure minus water vapor pressure and then use that that difference as when you subtract it in your math problem for PV equals nRT. Again, temperature for gases, it doesn't matter What else they're talking about? If temperature is the same for all gases, they all have the same average kinetic energy. And then again, it moves on to like non-ideal gases, which we call real gases. The parameters where gases behave most like real gases is at low temperature and high pressure. And under the same conditions, the stronger IMF attraction between gas particles, the less ideal the behavior. So when you have like a polar gas molecule like water that are able to come in close contact with one another, they actually could be slightly attracted to each other instead of hitting the sides of the container. Again, here's just a review of the individual gas laws. You don't have to know their names, but you do need to know the relationship among these. Expect to write a net ionic reaction or pick out a correct version of a net ionic reaction as a multiple choice question. You need to know what the spectator ions are and why we don't include them in the net ionic. There are very few solubility rules you actually have to memorize. Group 1 metallic ions are soluble nitrate ions, ammonium ions. Make sure you know those. Know your 6 strong acids. Anytime we'd write those in a reaction, since they are strong acids, they're strong electrolytes, we would write them as separate ions. So really only H plus from the strong acid would be in the reaction. Typically their conjugate base, their anion associated with that would be a spectator typically. Weak acids and bases dissociate very little, so in a reaction we would always write them as a whole molecule. You also need to know about oxidation reduction. You might use one of those mnemonic devices to remember what's going on there. So losing electrons is oxidation and gaining electrons is reduction. Always make sure a reaction is balanced for atoms, and if they're ions, like in a net ionic reaction or a redox reaction, make sure the charges on both sides of the reaction are also balanced. That can be a common mistake. Here's an example to try. You have a sodium chloride solution added to a solution of silver nitrate. Again, the term solution is telling you that these two compounds are dissolved ions in a solution. You're supposed to realize that you would not write the entire formula for either one. Both of those reactants would actually be 4 separate ions. It's telling you precipitate forms, and based on the few solubility rules you have to know, you should realize that the nitrate compound or even the sodium ion compound, both of those are covered in the solubility rules. You should know those would be separate ions as products, and the precipitate would have to be deduced to be silver chloride. So there is maybe a double replacement. It's a good idea to write that, to think about what's going on. I mentioned the 4 separate ions. The net ionic would be removing the spectator ions, the 2 ions that are staying dissolved, which are the sodium ion and nitrate ion. And the reason we would not want to include them in the net ionic equation is because they are not reacting, and we want to show only what is actually reacting in the solution. Here is a redox titration. This is just a common example. I gave you the permanganate ion plus the iron 2+ ion reacting in an acidic solution. Typically here, it's a question where you need to use a mole ratio. It'll ask you some math question, and they're looking for you to realize that you would use the coefficients in the balanced chemical equation to decide how much of one reactant is needed to react with another, or maybe even to form a product. In that first bulleted point, note the term standardized titrant or standardized solution. If you ever see that, just know that standardized means that we know the exact molarity of a solution. Gravimetric analysis sounds a little complicated. It really is about measuring the mass of something. So for our purposes, it's pretty common to do a reaction that forms a precipitate, a solid product, which we would want to filter out of a solution, dry it, mass it, and then answer some question about it. So I've kind of given you an example. This Buchner filtration system could be used. Usually you use like a vacuum pump to like speed up the filtering. Gravity filtration with just a regular funnel and a piece of filter paper works as well. It just takes longer. The key here is that we need to make sure all the water is removed, so that would not contribute to the mass of the solid. So maybe we dry it in an oven or leave our filter paper out overnight in the lab. But again, you can just go through those major steps of that. And here's that collecting a gas over water. I gave you just an example of a setup. There are many setups that could be given. You see there's a balanced chemical equation. It's a decomposition reaction. You're given a mass of the reactant. It says it completely decomposes, so it's completely forming the two products, potassium chloride and oxygen gas. And the question is, what volume of oxygen gas will be collected? Again, there's lots of information given. It's asking that question, but then it tells you atmospheric pressure. It tells you the vapor pressure of water, which when you see that, should kind of ring a bell that you've got to use that in your calculation. But the first thing, you should think about is, since we are given a mass of a reactant, oxygen gas is in the reaction with it, hopefully that would get you to go, okay, grams. If I have grams, I'm going to change into moles, but I need moles of something completely different, so then I do need my mole ratio. So you can see that's what I've done in number 1. And then, obviously I'm not finished because the question is about volume of this gas. Hopefully with the vapor pressure and the different details of this reaction, it would help you to realize you need to work towards solving PV equals nRT. Notice I did subtract out the vapor pressure of water from atmospheric pressure. The R units in PV equals nRT are in Kelvin. Part of the units for R. So that kind of tells you all the units you need to plug into PV equals nRT. So again, I've changed 22 degrees Celsius to Kelvin. I've plugged into PV equals nRT. You can see that's the other version of R that's given on the formula sheet that's in torr, since I was given torr to begin with. Again, some problems would give you atmospheres as the unit, which we would use the other version of R, 0.08206. So you just kind of have to see what information you're given. I've done the math and ended up with liters or milliliters. It didn't specify which. You do not have to give both answers. I would just stop at liters and be finished. You would not want to give a second answer that was not asked for, because if you made a mistake in that calculation and miscalculated milliliters, you would not get that answer point.